Hello, today's lesson is going to serve as a quick review of how to find the nth root of radical expressions, being able to add, subtract, multiply, and divide radical expressions. So the first thing that I want to talk about is the essential understanding. And it says that corresponding to every power, there is a root. So what this is talking about is if we have 5 squared, we know that is equal to 25. Well, that's the power of 2. Well, its corresponding root is the root of 2. Well, the root of 2 we say is the square root. So if we reverse this equation, we could take the square root of 25 and we could get 5. So that is an opposite operation. Well, it goes on. So 5 to the power of 3, we have 5 cubed is equal to 125. If we reverse that equation, we know the cube root of 125 is also 5. Well, the cube root means what number times itself 3 times will give us our radicand. So 5 times 5 times 5 is 125. Now if we look at the next example, 5 to some power is equal to 625. Well, if we do 5 times 5 times 5, we get 125. Times it by 5 again is 625, and that would be 4 times. So 5 to the 4th power is 625. Well, if we had 625 and we wanted to express it as a power of 5, well, we would find that the 4th root of 625 is equal to 5. And that means 5 times itself 4 times will give us 625. So for every power, we have a corresponding root that we could reverse that equation and find. And using that concept, we can kind of come up with a rule. So we have if a to the power of n is equal to b, we know that a is an nth root of b. So we could rewrite this expression, or equation I mean, as a is equal to the nth power, or the nth root of b, Now, using that equation, we have a few rules. So if n is odd, or the index, so the index of my radical is odd, there is only one real root. Well, for example, so if we have the cube root of 64, we are asking ourselves what number times itself 3 times, the index is 3, so times itself 3 times will give us 64. Well, we can say that that is 4. That's the only number that when multiplied to itself 3 times will give us 64. We could also do the cube root of a negative 64. Well, this would be negative 4, because negative 4 times itself 3 times will give us a negative 64. Now, if we go to the next example, so we'll say if n is even, so the index, if the index is even, and b is positive, there are 2 possible roots of b. Well, our radicand is the b here. So we know that it's going to be the principal root and its opposite. Now the principal root, this is something that's pretty important for us to understand, is just the positive square root, or the positive root. Its opposite will be the negative root. So the square root of a positive 64, what number times itself twice will be 64? Well, we know 8 is. But is there another number? Well, this says yes, because we know that there are 2 roots. Its principal root, the positive 8, and its opposite, which is negative 8. Well, how, you ask? Negative 8 times negative 8. Negative times a negative is positive. 8 times 8 is 64. So we have negative 8 and a positive 8. So again, if we are taking the root and our index is even, we have to say plus or minus. So it's a positive 8 and a negative 8. Now, keeping that in mind, if n is even, but our radicand is negative, what's the square root of a negative 9? Well, we know square root of 9 is 3, and the square root of a negative number is I, the imaginary number. So we say there are no real roots of b if my index is even and my radicand is odd. Alright, so let's do a few examples of that rule. So find all the real roots of the following radicals. Well, our first example is the cube root of 27. So this means what number times itself 3 times will give me 27. So one way I can find the answer is by factoring these out into their primes. So 9 times 3 is 27. 9 can be 3 times 3. So notice we have 3 times 3 times 3. So 3 multiplied by itself 3 times will give us 27. Now, since the index is odd, we know that there can only be one real root. Okay, so if it's positive, it's going to be a positive root. So this is a positive 3. Now we look at the square root. We know that the index is even, and so we need to, if we factor this out, notice 6 times 6 is 36, so we know the square root of 36 is a positive 6, but since this is an even index, we know that this is the principal root, the positive one, and its negative is also a root. So we say plus or minus 6, because negative 6 times negative 6 is also a positive 36. Okay, so if we look at the fourth root of 81, our next example, what number times itself 4 times will give us 81? So if we factor out 81, well, first one, I'm going to do 9 times 9, and then each of these 9s can factor out to be 3s. So notice now I have 4 3s. So the fourth root of 81, 3 times 3 times 3 times 3 will give me 81. Also, again, this is a even index, so I know that the principal root and its opposite will be the radicals, or the fourth root. So I know plus and minus 3. All right, so let me look at the last one, the cube root of 216. Again, we look at this index, we know that it's only going to be a positive number, and if I factor this out, I'll find that 6 times 36 is a factor of 216, and 36 can be reduced to 6 times 6. So there's our 1, 2, 3, so there's 3 6's, and so it's a positive 6. But let's look at this. What if it was a negative 216? So we put in a negative. What do you think would happen? Well, this is quite simply a negative 6 then. Okay, so negative 6 times negative 6 is positive 36. Times negative 6 again would be negative 216. Alright, so let's look at how to add and subtract radical expressions. We have the two following formulas for addition and subtraction. So we have a times the nth root of x plus b times the nth root of x. So if the index here in this case is the n, and the radicand, which is the x's, are the same, we can add the coefficients, the a and the b. So we have a plus b times the nth root of x. Similarly, with subtraction, again, if the index and the radicands are the same, we can subtract the coefficients. So we'd have a minus b times the nth root of x. So let's do a quick example, and let's say we have 4 square roots of 5x minus 2 square roots of 5x. Well, if you look at the index and the radicands, they are the same, so we can subtract the coefficients. So we have 4 minus 2 times the square root of 5x, and 4 minus 2 is pretty simply 2, so we have 2 square roots of 5x. Now let's do an example where the radicands are not the same to start off with. Notice we have the square root of 12 plus the square root of 75 minus the square root of 3. Now, the indexes are the same, but the radicands are different. So we need to see if we can simplify each radical expression separately. So if I simplify the square root of 12, I know that the square root of 4 times the square root of 3 is the same as the square root of 12. And the square root of 4 is 2, so I can say this is 2 square roots of 3. So I do the same with the 75. Well, the biggest perfect square that goes into 75 is 25. So I have the square root of 25, and that goes in 3 times. So the square root of 25 times the square root of 3. And this is plus. So the square root of 25 is 5, and I have 5 square roots of 3. Well, the square root of 3 cannot be reduced, so I'm just going to bring that down, and it's minus the square root of 3. And so now if you notice, I have the same indexes and radicands, all square roots of 3. So now I can add and subtract the coefficients. So this is going to be 2 plus 5 minus, and the coefficient of that, since it's not there, is just simply 1. And so I have 2 plus 5 minus 1 times the square root of 3. 2 plus 5 is 7, minus 1 is 6, so I have 6 square roots of 3. Alright, now let's talk about multiplying radicals. So I have a times the nth root of x times b times the nth root of y. Now notice I don't have the same radicands. I have an x and a y, but I do have the same indexes. And this is something that we need to make sure the index is the same. But when I multiply radicals together, basically what I can do is I can multiply the numbers on the outside. So I would have a times b, and then the radical itself and the index will stay the same. So I'll have the nth root of, and then I'm going to multiply the radicands together. So I have x times y on the inside. So whatever I have, I multiply the numbers on the outside, or their coefficients, and then I multiply the radicands together. Okay, this first example that I'm going to show you is a binomial times a binomial. So we have 4 plus 2 square root of 2 times 5 plus 4 square root of 2. And when we're doing binomial multiplication, we know that we can use the FOIL method. So I'm going to first take this 4, and I'm going to distribute it to both of these terms. So I have 4 times 5 plus, and then 4 times 4 square roots of 2. Then I'm going to go to this 2 square root of 2, and I'm going to do the same thing. So I'm just distributing them to the other two terms in the other binomial. So it's going to be plus 2 square roots of 2 times 5 plus, now I have 2 square roots of 2 times 4 square roots of 2. Now I go through and I do the multiplication. Okay, and so I just start off from left to right. So 4 times 5 is 20. And then I have 4 times 4 square roots of 2. So now remember, multiply the numbers that are on the outside together. So I have 4 times 4 is 16. And then the radical 2 square root of 2 just comes along. Again, now I go to the 2 square root of 2 times 5. Again, multiplying the numbers that are on the outside. I cannot take this 5 and put it underneath the radical. So it goes 5 times 2 is 10 square roots of 2. And then lastly, I have 2 square roots of 2 times 4 square roots of 2. Again, multiplying the numbers on the outside. So 2 times 4 is 8 square roots, and then I can multiply the numbers that are on the inside. So 2 times 2 is 4. Now, we've got to go ahead and simplify this completely. So notice I have like radicals that I can combine. So I'm going to go ahead and do that. 16 plus 10 is going to be 26. So I have 26 square roots of 2. And this is 8 times the square root of 4. Well, 4, the square root of 4 is 2, so I have 8 times 2. And I can simplify that still further. So I have 20 plus 26 square roots of 2. And plus 8 times 2 is 16. And now I can combine my like terms again. So 20 plus 16 is going to give me 36 plus 26 square roots of 2. And there I have completely simplified. Alright, so let's look at the last part of what we're trying to learn today. So we have this, we're going to talk about dividing radicals now, or also rationalizing the denominator. Now, rationalizing the denominator means to make what's in the denominator rational. Well, that is not having a square root. So whenever we have a square root or radical in the denominator, we need to get rid of it. And there's a few different ways or methods of doing this. So this first formula or rule, we have the square root of a divided by the square root of b. Now this is also the same thing as taking the square root of a divided by b. And sometimes we can use this to simplify things without having to do anything too difficult. Now notice I'm taking the square root, so we could also say that the nth root. Okay, so this index must be the same. So the nth root of a divided by the nth root of b is the nth root of a divided by b. Well, let's look at this first example down here. I have the square root of 20 divided by the square root of 5. Now, by themselves, 20 and 5 are not perfect squares, so we would have to do something a little bit more difficult if we didn't know this rule. But we can say 20 divided by 5, that will reduce to what? Well, 20 divided by 5 is 4. And so we have the square root of 4. Okay, square root of 4 is pretty simply 2. Now let's do an example where this may not really help us out. So let's say we have the square root of 3 divided by the square root of 5. Notice 3 and 5 are not reducible, so 3/5, putting it into this form would not help us out. So we need to multiply this by our special form of 1 to get rid of the radical. Well, our special form of 1 is going to be a fraction, if you remember. And so we're going to multiply it by something over itself. And anything over itself is always 1. And what number times the square root of 5 will get rid of the radical? Well, when it's the square root, it's just itself. So we have the square root of 5 over the square root of 5. And now what happens? Well, we can use our radical multiplication. Square root of 3 times square root of 5. There's not really much anything on the outside, or coefficients. Basically, they're just 1. 1 times 1 is 1, so we don't need to write that. But then we can multiply the 3 and the 5 together and get 15. But when I multiply two square roots, it's something times itself. We have the square root of 5 squared. Well, the square root and its power, those are opposite operations, so they cancel each other out. So we're left with just 5. And so now, once we have this, we need to see if we can reduce this fraction. Well, the square root of 15 has no perfect square factor, so that is completely simplified. And this 5 can't reduce with anything, so we are done here. So let's do an example where we will have some reducing to do. Notice I have 4 divided by the square root of 50. Well, the square root of 50 obviously can be reduced. And 25 is the biggest perfect square that goes into 50. And it goes in twice, so I can reduce that to the square root of 25 times the square root of 2. We know the square root of 25 is just 5, so we have 5 square roots of 2 in the denominator. So we can rewrite 4 over 5 square roots of 2. Now we still have that radical in the denominator that we want to get rid of. So again, we're going to multiply it by our special form of 1. And we only are paying attention to the radical itself. We don't care about the 5 that's out in front. So we want to multiply something by the square root of 2. That will get rid of it. Well, again, it's just itself, so the square root of 2 down here. But again, we want to make it that special form of 1, so we put itself, square root of 2, over itself, square root of 2. Alright, so let's multiply the numerator. 4 times the square root of 2, again, keeping that 4 on the outside. So I have 4 square roots of 2. And now I multiply 5 square roots of 2 times 1 square root of 2. Right here, so 5 times 1 is 5. Square root of 2 times square root of 2, again, is square root of 2 squared. So those cancel each other out. And so we have left 5 times 2. Now notice that the 4 over the 2 now I have in the denominator, these can be reduced by a factor of 2. So the 4 will reduce to 2, and the 2 will reduce to 1. So now I can rewrite this as 2 square roots of 2 over 5. And that is completely simplified. Now, there are certain times when we have to rationalize the denominator using conjugates. Now notice here in the denominator we have 2 terms. Both of these have radicals. Now when we have a term or a denominator that has a radical and there's 2 terms in there, we have to multiply by what's called the conjugate. Now if you remember what a conjugate is it's the same 2 terms but with the opposite side or sign in between. So again, the same 2 terms, square root of 5, square root of 2, but we change the sign in the middle to a positive. And again, when we're rationalizing, we multiply by that special form of 1. So yes, the numerator has to be the same as the denominator. Now when I go through and multiply, I have 3 square roots of 2 and times the square root of 5 plus the square root of 2. So what I'm going to have to do up here is I'm going to distribute this, but I'm going to save that for a little bit later. And then now in the denominator, when I'm multiplying my conjugates together, remember this is a binomial times a binomial, so I can use the FOIL method. But I want to pay attention to something that's a little bit cool about conjugates. Let's multiply the outside terms together and then multiply the inside terms together. So if we multiply the outside, we have the square root of 5 times the square root of 2, which is the square root of 10. So that's the O of FOIL, sorry. And then let's do the inside terms together. So we have negative square root of 2 times a positive square root of 5 is a negative square root of 10. So now if we combine these like terms, notice these are opposites and they'll cancel out. So that is one of the keys of conjugates. We don't have to multiply the outside terms and the inside terms together, and we can just multiply the first and the last terms. And that is one of the things that will really help us out with conjugates. And we can do this pretty quickly now. So let's multiply the first two terms, which is the square root of 5 times the square root of 5, which is the square root of 5 squared. And then we're going to multiply the last two terms. So negative square root of 2 times a positive square root of 2. Now that's a negative. And then square root of 2 times square root of 2 is again square root of 2 squared. Notice that the square roots and the squares are opposite operations, so they cancel each other out. So we're left with 5 minus 2, which is going to be 3. Now, remember, I did not distribute that 3 squared to 2. Now, since I did not, notice 3 over 3 can reduce, so those both can reduce to 1 over 1. And I don't need to show the denominator when it's 1, so now I only have the square root of 2 times the square root of 5 plus the square root of 2. So now if I distribute that, I have square root of 2 times square root of 5 is the square root of 10. Square root of 2 times square root of 2, again, that's going to be squared. Square root of 2 times square root of 2 is just 2. And there I have simplified it using the conjugate.